If you don't know what a transistor is or how it works, I would encourage you to watch the video on transistors before you watch this video. Because we're going to assume that you know what a transistor is and basically how it works. And what we want to do is find out how a transistor can be used in our computer. Well, we do know that at their foundational levels, computers run on electricity. It's either flowing or it's not. It's either on or it's not. There is an entire branch of mathematics called Boolean Algebra that allows us to express logical processes using binary values, 1 and 0. And Boolean Algebra is a perfect way to represent the values of a transistor, the presence or the absence of electricity, on and off, ones and zeros. So we're going to talk about some of the basic Boolean operators first, and then we'll move on to how this relates to transistors. One of the basic Boolean operators is called the AND operator, and it requires two inputs. Let's say that we have a manual transmission car. In order to start that car, I would expect you to have a key in the ignition and simultaneously the clutch depressed in order for the car to start. So let's write a truth table to express that. Let's say that the first input is going to be the key in the ignition, the second one is going to be the clutch is depressed, and then the third one is going to be whether or not the car starts. The idea is that if I'm standing outside of the car, I don't expect the car to start, and I'm going to represent the negative to be 0. If I put the key in the ignition without depressing the clutch, I still don't expect the car to start. If I don't put the key in the ignition, but I do depress the clutch, I hope the car doesn't start, otherwise burglars are going to steal my car. But if I do get in the car and put the key in the ignition and press the clutch, I expect the car to start. This is the logical AND operator. It requires both statements to be true in order for the entire statement to be true. So let's move to the next one. The next one is OR. OR requires one or the other condition to be true in order for the entire statement to be true. For this example, we're going to imagine that we have a classroom that has two doors, one on the left and one on the right. And at each door there are light switches. So I'm going to call this light switch 1 on the left, and we're going to call this light switch 2, and then we're going to try to determine if the lights will come on. If we are standing out in the hall without hitting either one of the switches, I wouldn't expect the lights to come on. But if we come in the left door and flip the switches on the left door, I expect the lights to come on. If we go back out in the hall and then we come in the right-hand side door and turn on the switches, I would expect the lights to come on. And depending upon how the room is wired, if we come in through both of the doors and flip the light switches, I would expect the lights to come on. The OR statement says one or the other condition must be true in order for the entire statement to be true. Now the next logic operator is called the NOT. And what the NOT operator does is it just reverses whatever the input is. And so the example that I have for this is your mother and her birthday. So I'm going to say this is Mom, and this is Mom's present. So it is your mother's birthday, and you go over to her house, and she says to you, honey, don't you worry. You don't have to buy me a present. I would put this as a 0. If she says you don't have to buy me a present, you should run right out and get your mother a birthday present, or she's going to be very upset. Unfortunately, my analogy breaks down because if your mother happened to say to you, honey, you better go out and buy me a present, my NOT operator would say that you don't have to buy her a present. But in real life, we know if your mother tells you that she wants a birthday present, you're probably best served if you get your mother a birthday present. So my analogy breaks down, but hopefully you get the idea that the NOT operator just reverses whatever the input is. So what we're going to do is we're going to build on these 3 operators to come up with 3 additional operators. The next one is the NAND, or if you can imagine, it is the NOT AND. If I have a NOT AND, I can imagine that it's going to NOT the AND, which means that, let's come back to my analogy of the car with the key and the clutch to see if the car would start. Well, the AND operator would say that if I'm standing outside of my car, that the car doesn't start. But I'm going to NOT the output, and we're going to say that if I'm standing outside of my car, that it does start. Let's say that I turn the key, but I don't turn in the clutch or depress the clutch. The AND operator would say that the car doesn't start, but I'm going to pass that through a NOT, and the NOT AND would say that the car does start. Let me move the screen down just a little bit. All right, so if I don't put the key in the ignition, but I do press the clutch, the AND operator would say the car wouldn't start, but we're going to NOT the AND. And then finally, if I get in the car and I press in the key in the clutch, the AND operator would say that it starts, but the NOT AND or the NAND operator would say that the car does not start. So you'll notice how the NOT AND is the exact opposite or the reverse of the AND. We're also going to see that we have something called a NOT OR, which is a NOR. Just as it did with the NOT AND, the NOR is going to be the opposite of the OR. So let's talk about the light switches in the room. We're going to have light 1, light 2, and whether or not the lights in the room come on. If we're standing out in the hall, this means that the lights are going to come on. If we turn on one of the lights, this means the light will not come on. If I flip the other light switch, the lights do not come on. And finally, if I flip both of the light switches, the lights do not come on because we have NOTed the OR operator. So the last logic operator that we're going to talk about is the exclusive OR. In our OR operator, I want you to notice that I said, depending upon the way that the room was wired, if we came in both of the doors simultaneously and turned on the lights, that the lights would come on. This last operator is called the exclusive OR. And the exclusive OR said it has to be one or the other condition, but not both simultaneously. So the highly controversial example that I have of an exclusive OR is marriage. We're going to say that this is spouse 1, this would be spouse 2, and this would be whether or not you are married. So you can have no spouse and you are not married. You can be married to this person and not that person, and you would be married. You could be married to this person and you are married. But in our exclusive OR, you cannot be married to both of them simultaneously. That would be a 0. So in my highly controversial example of the exclusive OR, it has to be exclusively one or the other or neither in order for the statement to be valid. This is an example of 6 of the basic Boolean algebra logic operators. So next we want to find out how we can apply these Boolean algebra logic operators to our transistors.